Hello everyone, welcome to PCB Africa. We hope you are doing well. This is another session on PCB review with Dan Beeker, and I hope you guys enjoyed the previous one. Definitely, we are going to enjoy this particular one, so I want you to enjoy it. And anytime you come on our channel, don't forget to share the video. We want these videos to reach as many PCB designers as possible. So help us do that. And also leave your comments behind, which we will try and tackle in any next review. All right, so as we already know, Mr. Daniel Beeker is a principal senior engineer at NXP, a very great PCB designer and electronic system designer. In fact, you can check his profile up on LinkedIn, Daniel Beeker, and then other platforms too. All right, so today we're going to review a board that I'm working on. It's a server for my IoT METS station devices. So today we'll be reviewing the server itself, and I hope you guys learn a lot from this. All right, Mr. Daniel, please.
Hi, good day, everyone, and thank you again, Professor Obeng, for creating this platform and leading the charge forward to spread the knowledge of field-based PC board design. And I have a response to one of the comments someone made before about whether or not Eric should give me the control of the design tool. But what I found is because there are so many different tools out there, to be an expert in all of them is way beyond my capability. And I find that it's always much more effective when I can have the designer who's familiar with the tool and the circuit board to basically drive the tool. And then I just direct where we go and what we look at and how we define those three-dimensional structures that we're creating in order to manage those doggone fields. So again, my honor to be here. I'm honored and excited to be helping spread the teachings of my mentor, Mr. Ralph Morrison. One more commercial for that. If you want to learn more about Ralph Morrison, go to ralphmorrison.com. And there's some interesting facts there and some videos that you might be interested in. Like I said before, we lost Mr. Morrison in 2019 at the age of 94 and a half. So he lived a very long and productive life, but he tried for most of his career to convince people that energy travels in spaces, not the traces. And that's the most important fact to be able to understand and apply that process and that perspective to your circuit boards. You have to manage the plumbing where this energy moves. So as we go forward now, if you would share your screen with the design, we will start looking at first, of course, the board stack up, the foundation of the circuit board.
Okay, all right. So I want to share my screen one. Yeah. Okay. So let me quickly show the 3D model of the board. Please, can you see my 3D model?
Yes.
Okay. So it's a very simple system with a 4G LTE IC from Simcom 7600GH. That's what I'm using this time, and then a Raspberry Pi. Yeah, just that. So this particular system collects all the data from the other IoT sensors and then back them up on the cloud. So it saves locally, but if there is internet access, then it transmits it to a server in the cloud. So that's what this particular device do, what it does. Okay, so when we come to the stack up, it is a 4-layer board. And I actually employed what we did, the review we did in the last time. I employed those that I remembered. So this 4-layer ground pour on all the layers, and I routed the power. because I actually don't have much places with power. So I actually routed power with the plumbing, your divided pipe plumbing approach. Okay, so that was to make sure that power was going to where it was needed and not to flood the entire copper area with power. All right, so yeah, if you would like to take over.
Okay, let's just start looking at the board one layer at a time first, starting at the
Okay,
top.
so I'm showing the top layer right now. Let me also hide the technical layers. Okay, let me hide this, and then yeah, I think this is okay.
That's pretty clear, yes.
Yeah.
So this looks very nice. I'm seeing what are probably waterfalls, as we talked about before, with
Yeah.
interleaved power and ground where they're needed, or adjacent grounds next to the powers, in order to create more z-axis paths to connect the dielectric between layers 1 and 2, and the dielectric on layer 4, and in a lot of places between layer 4 and 3, because we use the ground flood as the bounding layer or the unbroken conductor that we use to manage the power distribution. So let's look at 2
Okay,
alone.
so 2 is just a
Solid
ground
ground.
plane, a solid ground plane.
And then 3.
Okay, so on 3, I have the
Routed
pole.
power
Yes.
and ground.
So they are parallel. They are parallel to each other. It's parallel with the ones on top.
Yeah. So the advantage here that Professor Obeng is creating is when you have a power conductor on 1 and a power conductor on, this is layer 3. Correct. On layer 3, then you have dielectrics between 1 and 2 and 2 and 3. So 2 parallel pipes. And then the other advantage is using 3 for routing next to 2 from 1 is you don't require ground transition vias in order to connect the dielectrics between the layers. When you have a ground plane that's between 2 signal layers, the dielectric layers are automatically paired. So when you do any type of conductor via that makes a hole in the ground copper on 2, that provides the space for the energy to move from the dielectric between 1 and 2 into the dielectric between 2 and 3. Now, in the case of power, what Eric has done is added more ground vias adjacent to more power vias. This just increases the number of parallel paths for the energy so that the connection between the dielectrics in this paired dielectric environment have the lowest possible impedance. And it basically makes that transition from one dielectric to the next invisible to the path of the signal. And it provides a lower impedance path. So the energy much prefers to do that movement between the layers as it finds places to be consumed. So this is a very powerful tool or process to use, especially if you can from power supplies. I know that most often there isn't this luxury, but what I find is on the input power circuit for most boards, from the connector to the voltage regulator, in that space, there's rarely any other signals routed. So you have the opportunity to go from the wiring connection to the voltage regulator with these parallel dielectrics and to improve that movement of energy from the first capacitor next to the wiring harness into the voltage regulator. That helps to reduce conducted and radiated emissions. So, and then the flooding of ground everywhere. If you don't need to route a signal, then you put ground there because that helps keep the energy that you're trying to control, the signals or the powers, those electromagnetic fields will stay close to where you want them to be, in the space between the routed conductor, or what I call the switched conductor, and the unbroken conductor or ground. This has become a very solid platform for this circuit board. Now let's look at layer 4.
Okay, layer 4 as the bottom layer, also flooded with ground, and then other SMD components.
Okay, so this is a great place to look from now. Layer 4 is the most difficult layer to route. Layer 4 is not referenced to layer 2. That's what a lot of people have believed for years. It's 2 dielectrics and a signal layer away from ground. So the idea is that any signal that you route on 4 that requires some special concern, whether that be a very fast signal or one that's carrying a large amount of energy, then you have to be conscious of the ground flood that you've provided on layer 3, because that's the only way you can achieve controlled impedance or higher energy capability, because it would be the space between the top of layer 4 signal or power traces and the bottom of the ground flood on layer 3. Every other signal will not be able to be very fast, because you don't have, if you don't have the ground copper flood on layer 3. So those signals must be routed very carefully with a coplanar ground trace, so that you create at least a space in the horizontal dielectric on layer 4 between the traces. You would have signal and then ground, and signal and ground is a good way to do that. And then, while it's not as good as a signal trace over a ground plane or a ground flood, it does provide some boundaries for the field, so that it will be bounded by the edges of the foil of the traces and the ground flood on layer 4. So I call layer 4 an orphan layer, because except in the cases where you do have flood on adjacent layer 3, then you must route every signal, if possible, with coplanar ground traces or ground flood. So from this point, to show where Eric's been able to achieve that, to create good transmission lines on layer 4 because of the adjacent flooding, if you could put layer 3 on also at the same time, please. So 3 and 4 at the same time.
Yeah, so I'm showing 3 and 4.
Okay.
Okay. Yeah, so the layer 3 is the pink one, and the 4 is the blue one.
Okay.
Unfortunately, I can't split them.
Can flip them so that 3 is on top of 4. Yes.
I don't think that is possible here.
Okay.
I have it. Okay, 3 on top of 4. That is okay. That's possible. Yeah, like this.
Okay, so we're seeing 3.
Yes. But
so the only routing on 3 is in this small region where you routed power.
Yes.
That's excellent. Okay, so what I want to highlight here is that leaves most of this layer behaving as if it was a ground plane. And the power supplies that are routed on this are adjacent to the ground copper on layer 2, so they're all well behaved. They're also a copy of the copper that's on layer 1, so that's where he's provided 2 paths for the energy, which reduces the impedance by 50% and increases the energy per wave cycle to 200% of what you would get from a single one. So this is the idea of reducing the number of wave cycles to deliver the energy. So if you have a bigger bucket, it takes you fewer trips to the well to bring water to fill your bathtub, for example. And that's exactly the way this behaves. So this gives us two buckets that are able to carry energy. They are big buckets because we've got fairly wide traces and very well-defined transmission lines. So now if you could flip them back again so that 4 is on top of 3, and you'll see that all the traces that he's routed on 4 are always over the ground flood that's on layer 3. So it gives you the advantages of a 6-layer board where you would have 2 solid ground planes. So in this design, layer 4 is no longer an orphan. It's a well cared for signal layer with good transmission lines. And then, so at this point, the board stack up is optimal for this design. And the only thing left to check is to make sure that when we have moved from the paired dielectrics on layer between 1, 2, and 3, any signals or power routed from 1 or 3 to layer 4, excuse me, will require ground transition vias to connect to the dielectric between 4 and 3. So this is where the final check would be.
Okay.
Go look on 4, and every place there's a signal via bringing the energy down the board stack is to make sure. So just layer 4 is all we need at this point.
Layer 4.
Just layer
Okay.
4. Yeah. And this is the final secret. And many of my customers' designs have failed because of this last piece of the puzzle. So if we look at layer 4,
Yeah, this is layer 4.
okay, so every place there's a via by itself, like to the right of your cursor and up. So there's one in the middle top of the board.
Here?
Up where you were just at.
Okay.
So right there.
Oh, yeah.
There is an orphan via. See, this
Yeah,
is
yeah.
this is the fine tuning. So this orphan via needs a friend. And what I try to do is encourage people to place the vias so that the annular ring, the keep out area, overlap. So that makes it so you can't route between them, and you have the best path between the dielectrics, between the top and the bottom of the board.
Okay.
So sometimes it means you have to move things around a little bit in order to clear a path. So a via fits very well in the left-hand quadrant about the 10 o'clock position.
Here.
Yeah, but move it closer.
Yeah, so I finally got a ground.
To try to overlap and make those.
So maybe.
Yeah. Well, there's a trace there. So yeah, so you can do that. And this is how you can do the final review before you go to fabrication. And then you just look through the board stack and make sure there's nothing routed between those two vias. So this is the thing, and the reason I focus on this is I have seen many times where a single missing ground transition via has caused EMC failures, and even sometimes functional issues, because that discontinuity caused by not having a close ground via would induce a signal integrity problem. And the idea is that if you don't put a ground via there, it will find the nearest one. So it will spread out through the board stack, and it will interfere with other signals around it as it tries to get from the space between 4 and 3 up to the space between 1 and 2 or 2 and 3, or back down again. So this is what we want to do, is go through, and I start on 4 because that's where you can see Orphan Vias.
Okay, great.
So there's right there to the upper right of your cursor, there's another Orphan Via right there. That one's an orphan as well. It gets there okay, but it doesn't go back down into the board stack.
Oops.
This is where sometimes you might have to move things around, and there's plenty of room to move that. Raspberry SDA can be pushed up and to the right, and that will then leave you plenty of room for the ground via to make the other signal happy. And I just want to make a comment. KiCad is your tool, correct?
Yes.
It looks to be a very powerful tool.
Come again?
I said KiCad looks to be a very powerful layout tool.
Yeah. I actually like it.
A lot of features. I'm very impressed.
I like it. I sometimes use Altium, but I usually use it when I have to do very complex stuff. But for most of the things that I do, KiCad is quite okay. All right, so I have my ground close. Okay, layer 1, layer 2, top and bottom. All right.
So this is this is the final process. Once we've established a good board stack up and placed ground flood wherever possible, the final step is to make sure that every place you see a via on 4, there has to be a ground via very close to it. Now, in this case, you've got a ground pin, but I would still put a ground via here next to that. Because you want to connect, this is the next step, is connecting all the pieces of ground flood that are isolated, is that you want to be able to put 2 connections to the ground structure in the board stack. So in this case, one of the connections is the pin, because that's a through hole via. The second one needs to be in that flag or small island of ground, so you get the 2 ground connections in every piece of copper minimum. And then my rule is, if you can't get to, is either move things so that you can get a second via in there, or you delete that piece of copper. You don't want to have it a ground on one side and then a length of copper, because that does present a potential space for field to be collected. And because by having a small stub of ground, it is a smaller 3-dimensional structures, physical structure. And the smaller it is, the easier it is to induce a magnetic field into that conductor, which then causes the creation of a electric field, and it starts to move through the board stack. So.
Oh, okay, great. All right, that's interesting.
And just another repeat, we talked about what causes crosstalk. Changing when a signal is being driven through a transmission line, at the wavefront, you have a changing electric field. A changing electric field will create a changing magnetic field in the signal trace conductor. It does also in the plane, but the plane is physically so large that the amount of magnetic field created is very, very small. But the magnetic field that it can create in a trace is much larger because it's physically smaller. So that, for example, you've got an array of traces horizontally on the board. So when a signal is moving through the top trace, it will induce a magnetic field in the trace next to it as the signal propagates down at the wavefront. Then that will cause there to be a magnetic field in the adjacent conductor, which is changing. That changing magnetic field will create a changing electric field in the space between that second conductor and the third one. Then that changing electric field will create a changing magnetic field in the third conductor, and it walks its way through the board that way. No magic, very simple behavior. Back to the one rule is that the magnitude of the shared charge is reduced by the square of the distance. So the amount of energy is reduced as we move away from it. And this is where if something's, and it's again, the amount of energy per square centimeter is determined by the switching speed of the driver. So that displacement charge density, the higher that is, the faster it's changing from one voltage level to the next, the higher it will drive the magnetic field in the adjacent traces. So if you have a very fast switching event, that's where you need to consider having more space between the traces in order to reduce the impact of that. And that's why if you look at most of the memories, very high speed signals are not 5 volts anymore. They're 1 volt or 1.5 volts, because again, you're reducing the magnitude of that switching energy, and that reduces the crosstalk. That's the result of the creation of the magnetic field in the adjacent conductors.
Okay.
Very simple stuff. And the fields are really nice. They always behave the same way.
Okay. I have some the GSM RF signals on layer 1. They are microstrips. So I don't know if you would give a comment on it. Let me show.
We can zoom in there.
So we have, this is a GPS antenna, 50 ohm impedance control line. But then I have to insert some capacitors in between. So I was wondering, this is supposed to be a 50 ohm impedance line, and when it meets the part of the capacitor, is there not going to be some reflection since there is a change in impedance?
There always will be when you change, anytime the three-dimensional structure changes. So the wavefront sees a different space, because that's all that matters. There will be reflections, depending on the frequency at which you're switching at. That determines how big a discontinuity it takes to cause a problem. And we talked about ringing a little bit before. If the distance between the driver and receiver, or the size of the discontinuity, is greater than a quarter wavelength, then the reflection will be 100% of the magnitude. And so you run the risk of having a second order reflection. A discontinuity this small would take an extremely high frequency, most likely not found on an FR4 printed circuit board, to make any difference in the movement of those fields. That's one of the things, and that goes down where people were talking about, oh, you can't have right angles, you can't have sharp corners. None of those discontinuities, because they do change the face of the wavefront. It sees a larger surface, so there is a change in density of the charge, but they're so small that you can't have that frequency anyway on a printed circuit board. You might get into some issues with the higher performance ceramic material if you're doing very, very high frequencies, but then you already are, you have some different guidelines to follow as well. So that's a good question. These are discontinuities. Again, anytime the wavefront sees a different shape in front of it, it will behave. If it's a lower impedance, you will have a drop. It'll have a reflection at a lower voltage. If it's a higher impedance, you'll have a reflection at a higher voltage. But as long as that space is what we call lumped, where you never exceed 100% of the voltage in the reflection.
Okay.
And that's why we got away with bad design rules for years. Everything was so large relative to the switching speed of the transistors, it was always lumped. So you could do really bad things and it didn't cause failures most of the time. Now
Okay.
we have things that switch very fast, and the structures on the circuit board are very small relative to those switching speeds. So you have to be very conscious of what is or is not lumped.
Okay.
So
Okay.
the important thing here is, in order to couple the maximum amount of energy from the antenna into the receiver and from the transmitter into the antenna, is to make sure that you keep those impedances matched as closely as possible, because that gives you the maximum amount of energy driving through there, because the little reflections do reduce the power that's going out there. I mean,
Okay.
in the case of a structure this small, you probably can't even measure it.
Okay. All right. So typical of GPS, I think the frequency is about 1500 megahertz. So does critical length of the trace come in here? Because this is an impedance control line, like I said, and I don't know whether the length, I have to probably calculate at what length it will be critical.
1500 megahertz, you said?
Yes, I think that's part of the range. GNSS.
Looking at my chart, 500 megahertz is about 2 inches. So it's all ratiometric. So we divide 2 inches by 3. So lump distance is just under an inch.
Wow. Then
these are tiny little discontinuities.
Yeah, I have, I think, 10 mm. Okay, 10 millimeter.
Yeah.
Yeah, I think this should do. This should do. If under 1 mm.
It's probably about, whatever 0.7 inches is lumped. And that's a conservative lump. That's my lump, which is 1/6 of the wavelength.
Okay.
So, a non-conservative or liberal position would be, basically, 3/4 of an inch. So these structures are invisible to the radio signal. And a lot of people get hung up on the frequency, and they think that 1500 megahertz or 1.5 gigahertz is something that's very fast. And in today's world, those are not fast signals. The RF signals are quite often not the fastest signals on the circuit board. Do you have any memories? Memories are in the range of DDR4 is 12.2 gigahertz. Because it's switching at 72 picoseconds. SerDes, PCIe, the Aurora debug interface, those things are all 60 picoseconds. And so you're looking at, closer to 15 gigahertz.
Okay.
For logic signals. So this RF stuff is slow mode. The structure is much larger. So it becomes easier to design the RF section than the digital section in a lot of cases. And that's hard for people to understand.
Okay.
The only other thing here is you've got your connector. This is a BNC for the antenna. Is look through the board stack and make sure that it's nice and clear between the 4 ground leads and the center conductor for your bringing your energy in and out of the board.
Please come again.
Straight through the board underneath the connector. That's can't route in there, obviously. So.
Yeah, I think I actually checked that. Yeah. Okay, yeah. So around the connector, there is no route,
Yep.
but the routes here are on the bottom and it's shielded by ground
Oh yeah,
planes.
they're not even close to what you're doing. So all the other the radio traces are on layer one. They're adjacent
Yeah.
to layer two. They are happy little traces. Your challenge is just to make sure that you know how wide those traces need to be based on the thickness of your dielectric to get
Yeah.
your 60 ohm transmission line.
I
And
did the calculations with a GLC PCB tool. I think I had about 0.293 for 50 ohm impedance trace.
yeah,
That's
those impedance calculators are all pretty good. And then when you go to fabricate your board, you want to also specify which of these traces are 50 ohms. And
okay.
then they will make sure to adjust the process, how to manage those impedances for you.
Okay. Okay.
One mother trick.
Wow. Wow.
And then, so your last check will be to look for orphan vias on 4,
And
and then
4.
to make sure that you don't have any copper flood underneath any of the series components, resistors, inductors, capacitors.
Oh,
You
okay.
can't flood underneath those because you need them, the body of those components, to see the energy that's in the dielectric between
Yeah.
this. If it's a component on 1, it needs to see the energy between 1 and 2 in that space. So the
Oh,
body of those components need to see the energy. And then
uh,
below your cursor is another example of a piece of flood that needs to have another ground tacked into it.
this one.
Yeah.
Okay. But it's under an IC. IC is exempted from the component that shouldn't have flood under them.
Right, but you got an isolated piece of copper, so either find a way to put a via in there or just delete it.
Okay. All right. Then I think I can put a VA here.
Yeah, that's fine. If you can't, every additional via you place to connect the horizontal ground copper increases the density of your Faraday shield.
Okay.
That helps to reduce the overall radiant emissions, reduces the conducted emissions by giving everything a better path. And from an ESD perspective, it makes your board more robust and able to withstand greater levels of ESD. On the bottom, let's see, that one you want to put that up towards yeah, up there. Those are nice. And then the bottom, there's a piece of copper coming across that's along the bottom here, bottom there. Wherever you can along the edges of the flood, you drop some ground vias to kind of bound
Okay.
it.
All right.
And then one up above that one, and then along there. Some people do stitching vias around the edges. It doesn't hurt anything, but it's not needed. But like what I just did with one of my boards is wherever there's the flood like this, is I'll wrap vias around the edges of the flood.
Oh, okay. Okay. Yeah, I remember the last review we did, I did the edge shielding with the VS, but this
And
time
then
I
there's an
decided
orphan
to.
via by itself there on the bottom of the board.
Oh, yeah. Yeah. I think I may have put something on the signal. Oh, yeah. Oh, yeah.
So I hope you're starting to get comfortable with this whole process.
Very, very.
And
Except routing without power playing is very difficult.
well, it works really well. You don't have
Yeah.
to have that. It gives you much more flexibility in your routing. And yeah, and you don't want to have vias where you don't need them. Absolutely.
Wow, this is interesting.
You're a plumber, you're trying to create pathways for the electromagnetic field to move
Yeah.
Again, when you go from 1 to 3, it's automatically connected.
Yeah.
We added more ground vias so that there were more paths if it was full power. And some of this I've worked with you, we've exacerbated some of the solutions just to make sure that people watching this will see this. And if you're doing, 500 milliamps, you don't need a waterfall. But if you're doing
Okay.
5 amps, you're going to need a waterfall.
Yeah.
Inter
This
power
particular
ground is that give you that structure that you need.
This particular board may be drawing about 6 amps. Because of the Raspberry Pi, they recommend a 2 amp, but I made it a 3 amp power supply. And the GSM2 can spike sometime to about 2 amps. So I provided a total of about 6 amps for the whole system.
That's where having those nice parallel dielectrics for connecting the voltage regulator to the ICs helps to improve. The other thing is just to make sure that you have the small capacitors at the component leads. So wherever there's a power input to an IC, you want to have a small package capacitor close to those leads because you want those depletion waves that are coming from the IC transistors to see that capacitor first. And then all that has to happen then is the bigger capacitors refill the small ones.
Yeah, I think I did that.
Excuse me.
I did that. So I have some small capacitors around my power ports. All right. So that is one here.
That's on the secondary side.
Yes. It's on the batteries in input power, and I have one on my solar panel. Where is it? Yep, here is
Those
it.
are fairly large capacitors.
Oh, okay. I think.
I guess the first one on battery needs to be small because its job is to catch noise on the power supply, on the wire.
Okay.
And we did the same thing for the input from the solar charger.
Yeah.
Excuse me, all of a sudden my throat is tickling.
Okay.
And then
Okay.
once you get to the bigger capacitors, that's where the energy is stored coming from the wire harness to the big capacitors. And then their job then is to supply the energy to the voltage regulators.
Yeah.
And the voltage regulator takes the energy from the big capacitor and stores it in the one on the other side of the voltage regulator integration circuit, the inductor capacitor. And then that capacitor is the source of energy for the ICs. And then in the region of each IC, you have a large capacitor that is filled from the output capacitor from the voltage regulator. And then its job is just to refill the smaller ones that are close to the IC pins. So you get a progressively smaller drop in voltage because each of these containers are bigger, and you take a smaller percentage of the energy, and the slope or frequency of the depletion wave is reduced by going from the determined by the geometry of the capacitors instead of the geometry of the IC transistors.
Okay.
Excuse me. And then we'll go into this in detail with the power supply class that we're planning right now.
All right. All right. I'm really looking forward to that training. That'll be awesome.
Congratulations. I think you made big progress.
Thank you.
The board has a solid foundation, which is critical. So many times the board stack up is creates a design that's just not capable of doing the work.
Yeah.
And in this case, because you've been able to create good transmission lines on all the signal layers, 1, 3, and 4, by your proper use of ground plane and ground flood, it's as good as it can be.
Wow.
Congratulations. I think it's
Thank
going to
you.
be excellent.
Thank you.
And then I know you may or
Thank
may not be able to build this board and do an A/B test, but I certainly think it was a great board to use as an example to discuss the process for analyzing a board design and the results. I think if somebody looks at the two different boards layer by layer, and maybe you put that into a PowerPoint, you can see the differences in the way the copper is used. And the final line is the copper is balanced. You taking very little copper off of the board. It
Yeah.
reduces the cost per board and because it increases your yield in fabrication. It reduces the amount of chemical that's consumed during the creation of this board, so it makes it greener. And then when you go to manufacturing, the board profile through the reflow oven is going to be more uniform, and you'll get better yields in your assembly process. And then because we've followed these rules, it will also be more robust from an ESD perspective. So it will be able to survive more abuse at the hands of a customer or user than it would be without following these rules.
Okay.
I think that's
Awesome.
good. Thank you so much for allowing me to be part of this.
Thank you, sir.
And
Thank you,
I
sir.
encourage everybody to take a close look at these two classes that we provided and think about the process as much as the design. You can take this process and use it for your designs and be able to achieve significant improvement in behaviors when you identify issues with the board stack up, with the routing of signals where they don't need to be, especially power, and the final use of the ground transition vias where they're required when you go to the orphan layer on 4. So thank you very much.
Thank you.
The
Thank you too,
time,
sir.
and everyone be safe and have a wonderful day.
You too. You too.